Chapter 14 starts the first of 4 chapters on probability. This first chapter, we are going to learn the fundamentals and basics, which are going to then be built upon in the later chapters. So if there's anything that you don't understand, make sure that you ask questions in class or set up a time during seminar to get some extra help. So let's start by looking at some basic vocabulary. The first vocab word is random phenomena. This is probably a word that you've heard before, but let's look at the mathematical term for it. It is a situation in which we know what outcomes could happen, but we don't know which particular outcome did or will happen. An example of this, the lottery. We know what numbers are in that drum for Powerball, but we don't know what numbers are actually going to occur when the Powerball is drawn. So let's look. What are some possible examples of things that we know exactly what the outcomes could be, but we don't know which ones will actually happen? Well, the first and the quickest ones that come to my mind are flipping a coin. When you flip a coin, obviously, there's only 2 options. It's either going to be heads or tails, but until you actually flip it, we don't know what the results are. Rolling a die. When you roll a die, there's only 6 numbers on it, 1, 2, 3, 4, 5, and 6, but we don't know which one's going to happen. We could talk about any sports game. You know who's playing. You know one of those 2 teams is going to win, but you don't know what team actually will. These are several types of things that exist in everyday life. We know what all the possible outcomes are. We just don't exactly know which outcome is going to happen. Let's look at the next vocab word. We're talking about the word trial. A trial is each occasion upon which we observe a random phenomena. So when we're flipping a coin, one single flip is considered a trial. When we flip it a second time, that is also a trial. So it's simply each particular occasion that is a random phenomena. Let's keep looking at some more vocabulary. An outcome. An outcome is the value measured, observed, or reported for each trial. So if you flip a coin and it comes up heads, heads is the outcome. If you roll a die and you get a 2, that is your outcome. Next vocab word, event. This is a collection of outcomes, and we notate events with capital letters. So the event might be rolling a coin 5 times. The outcomes of the 5 rolls are your event. The next and last vocab word for the moment will be sample space. Sample space is the collection of all possible outcomes of an event. If we are rolling a die, what are all of the possible outcomes? 1, 2, 3, 4, 5, and 6. That's an example of a sample space. So let's look at a couple of examples related to sample spaces. So our first example, I need you guys to pause the video for a moment and go grab a coin because we're going to do some flipping. Okay, so hopefully everyone has their coin. I've also have a coin and I've also flipped my coin. So the first example here, we're going to get a coin, doesn't matter what the denomination is, and we're going to flip the coin 4 times and simply record our data below. So when I flipped my coin, my 4 responses were tail, head, tail, and tail. So based on just those 4 outcomes, Part B would like us to know what's the probability of a head according to my results. Well, my results say that the probability of a head is 1 out of 4 because I had 1 head out of my 4 flips. It also wants to know what is the probability of a tail. The probability of my tail is 3 out of 4. Now, we're going to take that same coin and we're going to flip it an additional 6 times. So my results are now another head, a tail, a head, and a tail. So now we would like to look at what is the probability of a head and a tail with the original 4 plus our new 6. So now, if I look at my results, I have 1, 2, 3, 4 total heads out of 10. That gives me 2 out of 5, or 0.4. We're going to do the same thing for tail. For tails, I now have 1, 2, 3 original, plus 3 more, which is 6 out of 10, or 3 out of 5, or 0.6. Finally, we need to flip that same coin 10 additional times and record our results. So my results were head, tail, tail, head, 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 tail, tail. And so now, finally, we want to calculate the probability of a head and a tail based on our original 4, then our next 6, and finally our last 10. So I had before 4 heads, and I just rolled 1, 2, 3, 4, 5, 6 more. So now my probability of a head is a total of 4 plus 6 is 10 out of 20, which is 1 out of 2, or 0.5. My probability of a tail, I had 6 before. I just got 4 more, so that's also 10 out of 20, which is 1 out of 2, or 0.5. So if you notice, every time our probability got a little better. Because we all know that when you flip a coin, the probability is 1 out of 2. Well, the first time around, it was 1 out of 4, which was 0.25, and 3 out of 4, which was 0.75. Then it became 0.4 and 0.6, and then it became 0.5 and 0.5. That is not a coincidence. That leads us to our next slide. Independent events. This is our next vocab word. Independent events are 2 events that they're independent if the outcome of one doesn't affect the outcome of another. So if you think about the coins we were just flipping, is it possible to get 10 or 12 heads in a row? Absolutely. Is it completely likely? Not so much. So an independent event, those are independent. It meant that the first head and the second head and the third head were not affected by one another. It means that yes, you can keep getting heads over and over and over again until eventually a tail comes up. Our next vocab word, law of large numbers. This applies to what we were just looking at. As the number of trials increases, the long run relative frequency of repeated events gets closer and closer to a single value. In layman's terms, the more we repeat a random phenomena, like flipping a coin, the closer and closer your probabilities are going to get to a fixed number. And that fixed number is what we refer to as the empirical probability. This is not the real life hands-on probability. This is the true mathematical probability. And so we know for certain that the probability of getting a head on a coin will always be 0.5. And we know that the probability of getting a tail on a coin will also always be 0.5. And as you saw, the more times we flipped the coin, the closer we got to that value. Law of averages. This is something that many gamblers believe exists, but it's not an actual real thing. Many gamblers, especially people who play games like roulette or craps, they bet on numbers that haven't come up in a while, mistakenly believing that they are due to come up soon. This concept doesn't actually exist. Just because a number hasn't popped up in a while doesn't mean that it is due. So many people think the same way when, for instance, a good baseball hitter has, say, struck out 6 times in a row. That doesn't mean that they're due for a hit. It'd be nice, but it doesn't mean that they are due. So just because, for instance, you get 7 heads in a row on a coin doesn't mean that a tail is automatically due up soon. So theoretical probability. This is really what we are going to be studying. We don't care about actually flipping the coins and seeing what the results are. We have a theoretical probability that exists. And so theoretical probability is probability that comes from a model. Okay, these outcomes should all have an equally likely chance of occurring. For example, flipping a coin, head and a tail both have the same possibility. Rolling a die, the numbers 1 through 6 each have the same possibility. Drawing a card, all 52 cards have the same chance of happening. It is very helpful to know when you're talking about theoretical probability what the sample space is. So when you're talking about theoretical probability and you have a sample space, here is our formal notation for probability. The probability of event A happening, remember we mentioned events are noted with capital letters, equals the number of outcomes in A divided by, so these are the outcomes that are good, they satisfy what we want, divided by the number of possible outcomes. These are the outcomes in the sample space. So if we're asking what's the probability of rolling a 2 on a die, well, how many numbers are actually 2s? Well, that would be 1. And how many possible outcomes are there on a die? Well, there's 6 different options. So the probability of rolling a 2 would be 1 out of 6. That's how that little formula works. So let's look at some more examples. Suppose we are flipping 2 coins at the same time. So let's say one of them is a penny and one of them is a dime. What is the sample space for this event? The reason I said one's a penny and one is a dime is you need to think separate. So it could be that both the penny and the dime pop up heads. It could be that both the penny and the dime pop up tails. Those are the two that most people are fine with. But then the penny could be a head and the dime a tail. Or the penny could be the tail and the dime could be the head. Now, we are going to use this sample space to answer a probability question. What's the probability of getting 1 head and 1 tail? Well, these are our possible outcomes listed for example 2. There's no other possibilities. So we know the total number of outcomes is 4. Well, how many of those outcomes have 1 head and 1 tail? Well, that would be this one and that one, which means that's 2 outcomes out of 4 that have a head and a tail. And with probability and fractions, one thing we always do is we reduce. 2 out of 4 reduces to 1 out of 2. That would be our probability. That is why sample spaces can make it very easy to answer these questions. Let's look at the next set of. So for each of the following, we're going to list the sample space, and we are going to tell whether we think those events are equally likely. So we are rolling 2 die. Obviously, each die has the numbers 1 through 6 on it, and we are recording the sum of the numbers. And hopefully y'all remember sum means adding the two numbers up. So if you think about rolling 2 dice, obviously the smallest numbers are 1 and 1. So 1 plus 1 is 2. Well, we could also have 1 plus 2, which is 3, 1 plus 3, which is 4, 1 plus 4, which is 5, 1 plus 5, which is 6. Well, can we go any higher than that? Well, sure. 2 and 5 make 7, and 2 and 6 make 8. We have 3 and 6 that make 9. We have 4 and 6 that make 10. We have 5 and 6 that make 11. And we have 6 and 6 that make 12. So we need to know, are every single one of these sums have the same chance of coming up? The answer to that is no. And here's why. 2, this number 2 right here, the only way to get a 2 is 1 and 1. There's no other possibilities. Same thing with 12. The only way to get 12 is 6 and 6. However, I'm going to use 8 for example. Well, 8 could be 4 and 4 on a die. It could also be 3 and 5. It could also be 5 and 3. And yes, remember, these are 2 separate dice. So 5 and 3 and 3 and 5 are both possibilities. So as you can easily see, 2 and 12 have way less of a chance of happening than the number 8. So these are not equally likely. So a family has 3 children. We want to record each child's sex in order of birth. So there's several possibilities here, and we want to definitely do this systematically. So the first situation is, what if the family has all boys? 3 boys in a row. Well, there's also the possibility where there's 2 boys and the third one's a girl. Now, if you notice, though, we're focusing on the order of the birth. So that one girl could have been the middle child. That one girl could have also been the oldest child. So you notice how I'm systematically, I did all 3 boys, then I did all situations for 2 boys and 1 girl. Now I'm going to do all situations for 2 girls and 1 boy. So that 1 boy could be the baby. That 1 boy, whoops, let me erase that. That 1 boy could be in the middle. And that 1 boy could be the oldest. So we've now exhausted all possibilities of 2 girls and 1 boy. Now our final option is all girls. So there's our situation. Now the question is, are each of these equally likely? The answer is yes. We can't control the order of the children, and every single boy and every single girl has exactly a 50-50 shot of happening. And remember, the first boy doesn't stop you from having a second boy or a third boy. So these are all equally likely. Finally, we are tossing 4 coins, but notice we're recording the number of tails. So I don't care about the order, I just want to know how many. Well, we could definitely have 0 tails. We could definitely have 1 tail, 2, 3, or 4 tails. The question becomes, are they equally likely? Well, the only way to have 0 tails is to have all 4 of them come out to be heads. The only way to have 4 tails is to have all of them come out to be tails. However, for example, 1 tail. Well, that 1 tail could be the last one. That 1 tail could be the first one. The 1 tail could be some of the middle ones. So obviously there's more cases for 1 than there are for 0 and 4. So these are, again, a situation where they are not all equally likely. Okay, so let's look at one more set of examples before we look at some probabilities. Suppose you are rolling a single die. Find the following. So one die. So first of all, let's go ahead and write out the sample space. We know when we roll a die, there's only 6 options. 1, 2, 3, 4, 5, and 6. So of those 6 options, what's the probability of rolling a 3? Well, there's only 1 3 out of the 6 numbers. That's a reduced fraction, and that is finished. What's the probability of rolling an even number? Well, you need to know that an even number are the numbers 2, 4, and 6. So that's 3 options out of 6. That, however, is not reduced. That would reduce to 1 out of 2. What's the probability of rolling a number less than 5? Well, all the numbers less than 5 are 1, 2, 3, and 4, which is 4 options out of 6. Those can both be divided by 2. That leaves us with 2 out of 3. So that was some basic probability questions. Let's look at some formal probability rules now. So we have some formal probability rules. The first and easiest is all probabilities must be a number between 0 and 1. Now, what's important to know is you can have an answer of 0. If an event cannot happen, its probability is 0. That would be this guy right here. And if an event will definitely happen, its probability is 1. But you cannot have anything lower than 0, and you cannot have anything higher than 1. The probability assignment rule. This says the set of all possible outcomes of an event, in other words, the sample space, must have a total probability of 1. So when you add them all up, they must equal 1. This right here is another way of saying it. The probability of the sample space is 1. Let's look at some of those in action. Many stores run secret sales. Shoppers receive cards that determine how large a discount they get, but the percentage is revealed by scratching off that black stuff, whatever that is, only after the purchase has been totaled at the cash register. The store is required to reveal in the fine print the distribution of the discounts available. So there's 5 options listed below. Which of these probability assignments are legitimate? So the probabilities, you either are going to get a 10% off, 20% off, 30% off, or 50% off discount. If you look at option A, 10% has a probability of 0.2, 20% 0.2, 30% 0.2, and 50% 0.2. Well, here's the problem with A. 0.2 plus 0.2 plus 0.2 plus 0.2 is equal to 0.8. This cannot possibly be a legitimate situation because remember, according to option number, our probability rule 2, they have to add up to 1. So let's look at B. We have a 50%, a 30%, a 20%, and a 10%. Well, 50 plus 30 is 80, 80 plus 20 is 100, and 100 plus 10, this comes out to be 1.1. Well, also, according to that same rule, the sums have to be a total of 1. So that also doesn't work. Let's look at C. We have an 80, a 10, a 5, and a 5. Well, 0.8 plus 0.10 is 0.90, plus 0.05 is 0.95, plus another 0.05 makes us a nice, perfect 1. So this is absolutely a legitimate option. Let's look at C. We have a 0.75, a 0.25, a 0.25, and a negative 0.25. This right here should scream to you a problem. Probabilities are not allowed to be negative, so that would rule out D. Finally, we look at E. 1 plus 0 plus 0 plus 0. Well, it does equal 1. There are no negatives. There are no numbers larger than 1. And so this is also a legitimate situation. However, it's not the best because you're only saving 10%. But it is possible. Let's finish looking at one more probability rule and that is the complement rule. Not complement like you look pretty. This is complement. This is a math term. It's the outcomes that are not in event A. So if, for instance, you are rolling a die and you want to know what's the probability of rolling a 2, you want a 2. The complement would be everything you don't want. So the complement would be 1, 3, 4, 5, and 6. The notation for complement is A with a little c in the exponent. So this would, for instance, be A. This would be A complement. The probability of an event occurring is 1 minus the probability that it doesn't. In other words, the probability of A is equal to 1 minus its complement. This is helpful when you have very large problems. Sometimes it's easier to find this one. And so if you can find that one, you subtract from 1 and you're left with the one that you're wanting. So let's just look at a couple of last examples before we're done. Suppose you are pulling a card out of a standard deck of 52. Find the following. Well, if you're unfamiliar with a deck of cards, you'll definitely want to go look online for a picture of a deck of cards or pull out a deck of cards because it will make these kinds of problems easier. We want to know what's the probability of drawing a king. Well, every single card, there's 4 of them in a deck. So that means that there's 4 kings in the deck out of 52. If you are not good at reducing, remember your yellow calculators, all you have to do is do 4 divided by 52, math, enter, enter. But this reduces to 1 out of 13. What's the probability of drawing a diamond? Well, if you remember, there's 4 suits, hearts, diamonds, spades, and clubs, and each suit has 13 cards out of 52. And so this, again, if you divide and do math, enter, enter, reduces to 1 out of 4. Finally, what's the probability of drawing a black card? Well, the spades and the clubs are black. So there's 13 of each, which is 26 total out of 52. That's exactly half your deck. And one final set of examples. A bag contains 5 red, 6 green, and 4 blue marbles. You draw a marble at random. So first of all, we have 5 blue plus 6 green, 5 red plus 6 green plus 4 blue, which makes 15 marbles total. What's the probability of drawing a green marble? Well, there's 6 greens out of 15. Those are both divisible by 3. That reduces to 2 out of 5. What is the probability of not drawing a blue marble? This is your complement. We do not want blue. So we know there's 15 total. We're going to take away the 4 blue ones, and that leaves us with 11 out of 15 that we want. That's how the complement works. You take the total, which was 15, subtract off the ones that you don't want, which were 4, and that leaves us with 11 out of 15, which is reduced. And so this is the end of your first video. We will be working on your homework, which is a worksheet, when you get to class. See you in class.